Hi everybody, welcome. This is lecture 2. Today I want to wrap up double integrals and get started on polar coordinates. So let's get to it. So at the beginning of today's lecture, I want to do a sample calculation. So here's the setup. The function we'll be integrating is f of xy equals e to the x plus y. And we'll be doing the integral over this region over here, this triangle, the region bounded by the triangle with sides, with vertices at 0, 0, 1, 1, and 2, 0. So let's compute that integral. So we're going to do it. So we want to evaluate this, not e to. Let me just plug in the formula for f of x, y. Okay, so we're going to do this. So last time we did this integral in the order dy dx. So with the outside integral was in x, and the inside integral was in y, with respect to y. Today, let's do it the other way around. So let's set this up as an integral in the order. Let me just give myself a little bit more room. Let's set this up in the order dx dy. So we can do the integral in any order we wish, and the result doesn't depend on the order. But the bounds that we have to that we use depend on whether we have dx dy or dy dx. So let's work the bounds out in this example. So in this example, first we're doing, if we have a dy outside, first we're doing an integral. So the outermost integrals with respect to y, and there the bounds. So the lower bound is the smallest value of y in this whole shape. So in this example, the points which have the smallest y value are the points in the x-axis where y is equal to 0. So let me put that in. So y starts at 0, and it stops. So right here, right? Y. So this point up top is the point in this region where y is has the largest value possible. So the upper bound for y in this example is 1. Okay, so now let's fix an intermediate value of y between 0 and 1, and let's work out the bounds for the inner integral. So if I fix that value, so x will be integrating from something to something else, right? So if for an intermediate value of y, x starts here and moves all the way to this other side. So the x integrals over this red interval, but we need expressions. So we need to know what this value, this lower bound for x is in terms of y, and what this upper bound for x is in terms of y. You see, if I had chosen a different value of y, I would get a smaller or perhaps larger interval. So these bounds for x depend on the y I fixed. So let's find these things exactly. So first, let me find an equation for this side. So this is a line. It passes through the origin. It passes through 1, 1. So I guess I'll just guess a formula and check that it does these two things. I guess y equal to x is a line that satisfies these conditions. It goes through the origin, goes through 1, 1. So a line is determined by 2 points. So this is the correct equation for the line. And here, let me find an equation for this other line. So let's see. So it contains the point 1, 1. So I see the slope is negative. It's actually -1. You move 1 unit to the right, and the value of, so x increases by 1, and the value of y drops by 1. So the slope is -1. So this equation is y equals something, well, something minus x. And the value, so if I want, so when x is 2, y is 0, so this something must be 2. Okay, so that's the correct equation for this other line. Now, so do we have what we want? So we want to know what x is over here in terms of y. And here, x is, by this equation, x is actually equal to that value of y, to the fixed value of y. Okay, so that's good. Let me do everything. Oops, sorry. Let me do everything in red. So x starts at y at the left, and it stops. Oh, I erased something I didn't want. And it stops on the right where x, so I have to solve the equation on the right in terms of x. So I just move x to the other side, and then y to the other. Okay, the equation looks exactly the same, but with the variable swapped. But I guess we were lucky here. This doesn't happen normally. We always have to solve for one variable. Sometimes we need to solve for one variable in terms of the other, and most of the time the solution won't be the problem itself, won't be the equation we were solving for. We were solving to start with. Okay, but so at the right, x is equal to 2 minus y. So you see we set up the double integral, now the two iterated integrals, and now we can integrate them. We can evaluate them. So let's do it. This is going to be an integral. So first, the outside integral stays still. So integral for y going from 0 to 1. Let's evaluate the integral inside. So what's the integral of e to the x plus y dx? I think this is e to the x plus y. Right, because if I differentiate this with respect to x, I get the derivative of e is e itself, e to the x plus y times the derivative of x plus y with respect to x, that's just 1. So so e to the x plus y, differentiated with respect to x, it gives me back e to the x plus y, so that's the primitive. We have to evaluate that with x between y and 2 minus y, dy. So this evaluation over here, so this is a function of y we're integrating. This is really e to the, so first we substitute 2 minus y in place of x, that's e to the 2 minus, and then we substitute y in place of x, e to the 2y. Like that. So the integral is the integral of from 0 to 1 of e squared dy, that's just e squared times 1, minus the integral of e to the minus y, e to the 2y dy, that's e to the 2y over 2, right? If I differentiate e to the 2y over 2, I get e to the 2y, evaluated between 0 and 1. That's, maybe I could have left the evaluation to do it the second step, so I could have done this. Let's leave the calculation. Let's do it one step at a time. So the result is e squared minus e squared over 2 minus, and then you plug in 0 everywhere. You get 0 minus e to the 0 over 2, that's 1/2. So the final answer is 3/2. Oops, it's 1/2 of e squared minus, and then there's a plus a half. Okay, I'm sorry, the answer got a little squeezed there, but I hope it's visible. So there you go. We just computed another double integral, and this time, what was different today compared to the last lecture is that we did it in the order dx dy rather than dy dx. So if we were doing in the order dy dx, let's think about that for a while. There is actually a good reason why there's actually a good reason to prefer doing this integral in the order dx dy rather than dy dx. Even though you can also do it in the order dy dx, in that order the integral becomes a little bit harder. So let's think about that for a while. So let's look at the other order. Other order. So the double integral that we had before, over that triangle, r is that triangle, dA. If we were to compute it in the other order, so instead of dx dy, we had dy dx, it would be integral e to the x plus y, give myself some room over here, dy dx. So if we were doing it in the other order, so let's see what the bounds are. So first, let's look at x. So if we have dx outside, the bounds for x are, so the bounds for dx outside will be the minimum value of x in the whole picture and the maximum value of x in the whole picture. So that would be 0 and 2. So let's start doing it, but I warn you, we'll have to backtrack in a second. From the recipe I gave you, this interval would go from 0 to 2, and then we have an inside integral in y. Okay, now let's look at the inside integral. So if I fix an intermediate value of x, like here, and then the dy integral inside will be going up this vertical interval. And you can see that for every value of x, no matter what x I have fixed between 0 and 2, the y integral always starts at 0. So let's start the integral at 0 here. Now let's ask ourselves, where does this integral stop? So you see, from the value of x that I drew over there, you would say that that y is supposed to stop when it reaches this vertical line, the line where y is equal to x, right? So from this little segment I drew, you would say that the upper bound for the integral was x. So you would go here and write that y stops at x. But that wouldn't be right, because that would be saying that for values of x over here, right, the outside integral is from 0 to 2, that the y integral would be going too far. Instead of stopping where it's supposed to stop, it would continue all the way to the other line. So that's not what we want. So in this case, if we want to do the integral in the order dy dx, we should break the outer integral in two. The break point is here, where x is 1, because that's the moment when the rule where y is supposed to stop changes. So let's implement that. Let me break the x integral in two. So we have first the integral over the first half of the segment, and then another integral over the second half. So in the second half, x starts at 1 and stops at 2. And then, right, in the second half, x starts at 1, stops at 2, and y starts at 0 and stops at 2 minus x. Okay, so we definitely could evaluate these two integrals. The computation would be manageable, but it would take a little bit more work. So in this case, it turns out it's better to do the integral in the other order, if you want to save work. So sometimes doing the integral in one order is basically impossible. You can't find the primitive, but in the other order is manageable. So if you get stuck trying to do it in one order, you can shift to the other order and give it a try. All right, so let me just write this down. The takeaway here is that you can do, so this gives the same answer as before. Right, the number we got before was a half of v squared plus a half, and if I did these two integrals and added the numbers, I would get the same. I would get the same number. Okay, so this is it for what I wanted to tell you about double integrals. Now this is it for the second example. Now there's a final point I'd like to make about double integrals before we move on. I actually want to rectify something that I told you that wasn't quite true. It was almost true, but I simplified things a little bit. Let me show you what I'm talking about. So I prepared the slides here because it would take too long to draw and make this point, but it's really a simple point. It's really a straightforward thing. So what I explained, the integrals I showed you how to do in the first lecture was the formulas I gave you were right when we have a type 1 region. So it's not true for, you'd have to modify the formulas for more complicated regions, but for type 1 regions, the easy regions, the formula is right. So here's what a type 1 region is. It's a region it's the region of the plane that's between the graphs of two functions. So here I have the function g1 and the function g2, and our region is between the graphs of the two functions over a certain interval of the plane. Integral over a certain interval of the x-axis, right? So a type 1 region is a region of the form that I give you down here. So I'm looking at all points x, y in the plane, where x is in some interval and y is between the two functions of x. So the test for a type 1 region is this, it's the vertical line test. So if you fix a value of x in the x-axis and you intersect it with the vertical line, you should get a single segment. Then g1 of x, so if I fix x, g1 of x is the lower bound, the lower bound, the starting value for that y interval, and g2 of x is the upper bound for that interval. And when we have this set up, the integral I told you, the way to set up double integrals I gave you really works. Now, let's look at the integral. Now, let's look at integrals of other types, regions of other types. So here, if we try to use this formula on the region on the right, we end up with the problem, right? I would say maybe the minimum value of x in the whole region is here, the maximum would be here. But the problem is that the inside integral, which is supposed to go over a vertical line segment, wouldn't accurately represent the region. So this inside integral is supposed to go over a vertical line segment, but if I draw a vertical line on this region on the side, you'll see that the vertical line has two components. So this tells me that the innermost integral, if I were to do it in the order dy dx, would actually have I wouldn't have just a single integral, I would have two, one for each component. I would have two integrals over here, I would have a single integral over here, and here is the breaking point. So I would have to break out the outside integral in two and have, because of these two different regimens. That's not what you want to do. So for the region I have, the type 2 region I have on the side, it's much easier to do the integral in the order dx dy. So type 2 means that it's exactly the same as type 1, but with the roles of x and y reversed. So the region, instead of being bounded between two functions of x, it's bounded between two functions of y. So x is a function of y on the two sides, and y is in some interval, right? So we're looking at points x, y, where y is in some interval and x is in between two functions of y. And then in that situation, the formula I gave you last time, but in the other order, just works. Just gives you the correct number, the correct interval. Okay, so type 1 regions and type 2 regions are nice with respect to integration. And since we're talking about integration, I think it was useful for me to, I think it's a good idea for me to give you this terminology, so you guys can if you see this pattern, you have a name for it. So, now, I should make the point, final point here, that some regions are neither type 1 nor type 2, and then you might be, stuck about how to set up an integral for such regions. And the solution is that any region, even though not every region is of type 1 is of either type, you can always break it up into two regions, into a number of regions which are of either type 1 or type 2. So in this example, the whole region is not of type 1, because if I draw this vertical line, I get two segments. It's not of type 2. If I draw this horizontal line, I get two segments. But if I break it up in the way I just did, then this half, R1, is of type 1, and this other side here, type R2, is of type 2. And so I can set up these two integrals. So I would want to set up the first integral in the order dy dx and the second one in the order dx dy. Well, most likely. Okay, so so this is it. This now finally does indeed wrap up the comments I had about double integrals. So I recommend you work, do some practice problems to get yourselves familiar and comfortable doing these integrals. Let's now move on to polar coordinates. So here's the story. So first of all, what are coordinates in the plane? So coordinates are pairs of numbers, pairs of numbers, in fact, that we attach to points in the plane that we use to describe those points. The usual convention with Cartesian coordinates is that I give you, we agree at the beginning of the conversation that we have fixed axes, x and y in the plane. The point where those two axes meet is called the origin of the plane. The two axes are perpendicular, and then x is the distance from the y-axis, and y is the distance from the x-axis. Now with polar coordinates, we'll be using a different convention. So if I want to localize, so the axes are still there, but the, or at least the origin is, well, yeah, never mind, the axes are still there. But if I want to describe a point, I will give you two other, instead of giving you x and y, these two distances, I will give you two other points, two other numbers. The first number is the distance from the origin. And the other number, so here we have a point x comma y, the first number in polar coordinates is r, the distance from the origin, and the other number is theta, the angle around the origin measured from the x-axis to the y-axis. So let me draw this little arrow here to indicate the orientation. So here's how we relate the old variables to the new variables. So x is just r times cosine theta by looking at this square triangle over here. And looking at the same triangle, we get that y is equal to r times sine theta. So you see that if I know r and theta, I can find x and y kind of easily. I can also find, if I know x and y, I can find r and theta as well. That takes a little bit of geometry, of trigonometry. So for example, by Pythagoras' theorem applied to this triangle, which has a square angle, a right angle, r squared is equal to x squared plus y squared. So if I solve this equation, if I take square roots from both sides, I can find r in terms of x and y. And also looking at this triangle, you see that y over x is the tangent of the angle. So theta is the arctangent of y over x. So you can go back and forth. Now, in this class, we'll be using double integrals to, so polar coordinates to simplify integrals. So let me show you how to set up a double integral using polar coordinates. So here's the situation. We're going to have, so if we're integrating something, we're going to have some region R, and we'll be doing a double integral of a function, f of xy, over this region. So to do this, the integral is going to look like that, like this. It's going to be, we can do it as a double integral with respect to r and theta rather than x and y. I want to be generous with space. And then we have to write, so we're going to plug in some special correct values for theta and r, and we have to write everything, the whole integral, in terms of r and theta. So this means that whenever I see an x, I should write r cosine theta. And wherever I see a y, I should write r sine theta. And then you multiply that by dA. So dA in Cartesian coordinates is dx dy, but in polar coordinates is r times dr d theta. And this is the order that you normally want to do it in. So dr times d theta tends to be better. Okay, let's see how this works. So let's look at the bounds. That's usually the source of headaches. So the theta integral the bounds for the theta integral should be the range of angles that cover this region. So here you can see that the whole region is bounded by these two angles over here. This angle and that angle. Actually, let me draw that with a permanent way. So the whole region is bounded by these two angles. First one I'll call the minimum theta angle, theta min, and the other one I'll call theta max. Okay, and now when we do the inside integral with respect to r, we're fixing some intermediate value of theta, like this, and we're shooting out a ray. So we fix theta and let r increase. So r is always, oh, this is actually important. So in polar coordinates, we use the convention that r is always non-negative. Because otherwise there would be an ambiguity if I mean in theta, and theta is between 0 and 2 pi. Otherwise, theta would be ambiguous up to a factor of pi, up to adding 2 pi to it, up to adding pi to it. Okay, but going back to the inner integral in polar coordinates, so we fix an intermediate value of theta, and then we shoot out a ray with that intermediate value, and the lower bound for r is the radius where you first enter the region, and the upper bound for r is the radius when you leave the region. So this is going to be r min that depends on theta, and this is going to be r max that depends on theta. And the fact that so I think this all makes a good sense, but I still need to explain why dA is equal to r times dr d theta. So I'll do that, and then I'll do an example calculation, and that'll be that'll be everything I wanted to tell you today. So here's why dA is r times dr d theta. So first, a general idea why dA is r times dr d theta rather than just regular dr d theta. So when we do this, when we do the double integral with respect to, like, when we do this, the two integrals with respect to r and theta, we're really integrating a function, the original function, in terms of r and theta multiplied by r. Right. So this means that we're spacing, when we do these two integrals, we're increasing theta a little bit and increasing r a little bit at a time. So we're really doing breaking up our region into pieces like this. Right, dr d theta is area in the r theta plane, and if we're increasing theta and r a little bit at a time, we're drawing little squares in the r theta plane. But these polar squares, polar rectangles, they look different in the xy plane. So if I increase theta a little bit, I get different rays, and if I increase r, so if I look at a value of r, so fixed values of r give me circles, and as I increase r, I get larger and larger circles. Okay, so here's the reason I drew this picture. I wanted to point out that this little polar rectangle is much smaller and has less area than this polar rectangle. The farthest you are from the origin, the bigger these rectangles get. Let's be a little bit more precise now. So actually, before I be precise, let me emphasize the point. So the reason there is an R here is that this rectangle is smaller than that rectangle. Let's see how much smaller. So I prepared this picture beforehand. So the area of this, so we're assuming that we fixed the value of theta for this point, and we fixed R also for that point. And now we start with the value of theta and value of R, but we now increase R a little bit and increase theta a little bit, drawing this, tracing out this little polar rectangle. And our job is to understand what's the area of this polar rectangle. And it turns out it's approximately R times delta R delta theta, because, well, this length over here is just delta R. You can see that this length is the same as this length. Now this length over here is different from delta theta, right? So these angles are being measured in radians. So delta theta is an angle in terms of radians, which is the same as distance in the circle of radius 1. But in the circle of radius r, the correct distance is over here. So delta theta would be distance is an angle in radians. It would be the same as distance in the circle of radius 1. But in the circle of radius r, the correct distance is r times dr delta theta, r times delta theta. And so the area of this little rectangle, this polar rectangle, you can see it looks like if delta theta and delta r are really small, this is going to look like a rectangle, and this area is going to be approximately r times delta r delta theta. And this approximation is good enough when you do integrals. When you break up the region into a bunch of little pieces, a bunch of little polar rectangles, the error in this approximation that you make for each little rectangle, when you add up over all rectangles, that goes to 0 in some sense. Okay, now to wrap up today's lecture, let me do one more sample calculation. Let me show you how we use polar coordinates in practice in a simple case. I will show you a more sophisticated example at the end of next lecture, or at the middle of next lecture. So the function we'll be integrating is 1 minus x squared minus y squared, and the region is going to be a quarter disk. So this curve, my picture doesn't look too good this time, but this is just the disk of radius 1, the circle of radius 1, right? This is the set of points where x squared plus y squared is equal to 1. I could even put a square there. So this is a set of points where the distance from the origin squared is equal to 1. That's the same, that's the circle of radius 1. And I'm looking at the piece of it that lives in the first quadrant, so I'm asking that x and y are both at least 0. Now let's set up this double integral. This is the double integral over r of 1 minus x squared minus y squared dA. So this is a good integral to evaluate using polar coordinates for two reasons. First, because the region is going to be easy to describe using polar coordinates, and second, because the function can be neatly expressed in terms of polar coordinates. So you see that that x squared plus y squared is r squared, so this is minus r squared. So let's set up the integral. So there is going to be an integral in theta, an integral in r, and then you have 1 minus r squared. So that's the original function times dA, that's r times dr d theta. So to get ready to compute, we need to put in these bounds, fill in the bounds. So for this region, the angles are 0 and 90 degrees. So in radians, that's 0 and pi over 2. right? Theta goes from 0 to pi over 2 in this region, and r, if I fix an intermediate value of theta between 0 and pi over 2, I will enter the region immediately, so r starts at 0, and I will leave the region when r is equal to, in this case, 1. Okay, so now the geometry part is over, and it's time to evaluate this integral. So let's do it. Let me continue on the next page. So we have an integral in theta from 0 to pi over 2, and then an integral in r from 0 to 1. The function we're integrating is r minus r cubed dr d theta. So let's do it. So the theta integral will just be left outside. I won't touch it for the time being. The integral of r dr is r squared over 2. The integral of r cubed is r to the 4th power over 4. And then I evaluate this between 0 and 1. Now, if I evaluate the inside integral, I'm going to get a half minus a quarter. That's just a quarter. And then I'll be integrating a quarter from 0 to 2 pi d theta. That's just, if I integrate a constant, I get that same constant times the length of the interval. For the integral, that's pi over 2. So the final answer for that integral is pi over 8. So I could have, okay, let's stop and be happy that that we're done with the integral, and we got a nice number that looks right? There is a pi in there, but there's also a circle. There we have an explanation for it. I should mention that I could also set up this integral using Cartesian coordinates, but it wouldn't look as good. So let me just show you how this would look like. So I would have an integral in x going from something to something, y going from something to something, and then the original function, dy dx. Okay, so x would go, you see the points with the minimum value of x in the whole region are all here, where x is 0, and the point with the maximum value of x in the region is here, which is 1. So the maximum value is 1. So x goes from 0 to 1. For an intermediate value of x, y would go from 0 to the y value here, right? So if x is fixed, y would start at 0 for all of these x's, and would stop at a y value that depends on the x I fixed. Okay, but what's that value? Well, here you guys can see by solving this equation that y is equal to the square root, or plus or minus the square root of 1 minus x squared. It turns out that in our case we want the positive root because y is positive. Because I said that y is positive, so we just use the positive square root. So the upper bound would be root of 1 minus x squared. So that's it. This would be a more complicated integral because of this square root. Maybe you can do it. Maybe you do a trig substitution that would, in the end, be doing would be a less transparent way of introducing polar coordinates. So that's what I had to say in the second lecture. So thank you for listening, and I'll see you guys next time.